So I will be presenting in the next minutes this contribution on the stress fields and strut and tie models, which will follow the paper that you might find in the issue, which is named the Stress Field and Strut and Tie Models as a basic tool for design and verification in second generation of Eurocode 2, which I co-authored together with Linka Huang from Technical University of Denmark and Aurelio Muttoni from the Swiss Federal Institute of Technology in Lausanne. There you will find many details. Now I have to comply with the time that Jesus provides us. So I will just be giving some clues, some highlights on what were interesting changes, what were motivation for the changes in Eurocode 2 and how this has moved to a new provision. So to start with, what was the starting point? That starting point was what is the current, still current EC2, so the EN 1992-11, 2004. That was a strut and tie oriented, so it was very compact, 4 pages, and it was giving rules for the strut, for ties, for the nodes, for the verification of all the elements. Then it came I would say a period where we were thinking on if that required improvement, if there were new knowledge that was available and allowing to make a step forward in the consistency of those provisions. And then we observed that these provisions were good and consistent, inspired in a Schleich approach, basically in the 1980s. And since then, that many advances were consolidated. To start with, the analogies of strut and tie models and stress fields. This is something that was already known at the time, but I would say that the combined work with both of them was not that explicit. And that was something that could be introduced in a very consistent manner. We also see why. Then there was also the explicit consideration of the strain state in the calculation of efficiency factors. So what was provisioned in the current Eurocode was basically constant efficiency factors, so that were accounting for given levels of cracking, given states of cracking on the resistance of concrete. That was seen that with time, we can get a much more refined estimates on that in much more interesting ways when we can account how a structure is deforming, how a structure is cracking, to calculate how the forces are transferred, the stresses that can develop through the concrete. Finally, I think this point was already said by Aurelio Muttoni. There was also the intention to show in a very transparent manner to designers this transition between what is a deep region, so where the assumption of plane sections remain in plane does not hold true, and B regions. So to have a tool so that we can pass in this transparent manner from the design that we are carrying for B regions, so shear design, for instance, to what happens when we are coming to a discontinuity region, when we are, for instance, close to a support. I think that was also very nice aspect to be improve the consistency. And the basis for the revision, so the compilation of the state of the art at that time, was the one that was compiled in FIB in Bulletin 100, that was done by Working Party 224, that was already accounting in a very explicit manner for all these aspects. So that was, I would say, the document that was considered, and at that time it was in the process of being finalized, and that was being considered to improve the state of knowledge. So all of these came into the new provisions. So these are the provisions that you may find in the FPREN. These are, and you will notice, these are strut and tie and stress field oriented. So it is being dedicated at both issues, and also in the sense that you can go from one to the other. So they are not visions completely separated, but that you may work in some cases with one, in some cases with the other. You may combine them, and this is perhaps the most efficient manner to do that. The price has been that it has increased the size from 4 pages to 9, but it provides this possibility to develop strut and tie and stress field consistently. It is giving also these consistent rules for the shear design, and also it is opening the door to, as I was showing before, not only to do strut and tie and stress fields from rigid plastic perspective, so handmade analysis, but also to is really leading to introduce more advanced elastic plastic compatible stress fields that allow for much more interesting analysis, particularly in views of assessment of existing structures. So just to clarify also why we're seeing these strut and tie and stress fields, this perhaps it is good to highlight once again that they are, in fact, they are expressions in some sense of the same phenomenon, but they come from different historical origins. And this is why they have been even chosen as different schools and even different procedures to develop one or the other. The strut and ties, they come from the truss analogy already written or proposed by Ritter, and which is was based on an intuitive approach to how the forces were carried inside a concrete member, how the forces are transferred through the concrete and transferred through the reinforcement. On the contrary, stress fields, they were developed as an application of the theory of plasticity, formerly in 1961, and they were seen as limit analysis solutions. However, as you may see already in this picture, there are strong analogies, and in fact, they're not one solution or the other. The best is actually to work with both. Some time ago, many years ago, we wrote a paper in Hormigón y Acero, by the way, was in Spanish, where this possibility of working with both was actually identified as the best. Sometimes we are aiming at knowing what is the stress state in the concrete, just to, for instance, to verify nodal regions, and this working with the stress field is extremely efficient. Sometimes we are trying to design what is happening with the reinforcement, how many, what is the section that we need for the reinforcement. And this is perhaps more convenient to be done with the strut and tie. So working in a combined manner is always a nice step. And since then, I think what is the biggest step forward was to think that it is not only incorporating these rigid plastic considerations, but we can also do by accounting for compatibility of the formations. For instance, this is one possibility, and this allows to develop solutions which are going to the exact solutions according to theory of plasticity, but also that are consistent with rigid plastic analysis. So we are refining increasingly. This is what is called these levels of approximation, levels of refinement approach, and we are approaching more and more with a bit more of work to what could be the solution, the exact solution according to limit analysis. So in terms of what have been changes, I think that or aspects that are interesting to highlight in this revision of the code. First of all, we could speak about the compression fields and struts. And this, when we are determining what is the stress field, might be with elastic plastic analysis, might be with rigid plastic one. What is the stress? I think it doesn't change. It's the force that we have upon the surface. However, there has been, I think, a lot of work that has been devoted to the resistance. The resistance is composed of two parts. First one, it is what is called the design plastic strength, is FCD that you see here. And this design plastic strength is considering that the concrete is not a perfectly plastic material, so it is a softening after reaching the peak value. And so in a stress field, we are not attaining simultaneously in every dot, in every point, the maximum strength. So there will be regions that are at maximum, there will be regions that will be softening, and there will be regions that are still not attaining the maximum strength. So we are not considering the peak resistance, but we are considering what we call the equivalent plastic resistance. This term and consideration has already been introduced in today's by today's speakers. The other point is about the efficiency factor, this term called nu. And here, this is a long-term known effect on the compression softening. So the wider the cracks are, the less capacity the concrete has to transfer forces, to transfer compressive stresses. And there has been a number of formulations on that. Eventually, in the code, it has been adopted one formulation, which has been proved to work nicely for beams, for panels, for many types of structural elements. And this one is what we can call a local formulation. This is something that we can use locally in every element that we are having. So it depends, this new factor, this efficiency factor, is depending on the maximum tensile strength that we are having in the concrete. This, as you see, it is also aiming us that if we calculate what is the displacement field and the strain field, which is associated for a given level of load, this allows calculating what are the efficiency factors and evaluating in a very tailored manner what the resistance of an element might be. Also, this has opened the door to a very nice approach or consistency, I would say, with the shear verification. So by using the same assumptions or the same expressions, but by suitably evaluating what is the average level of strain that we are having in a web which is subjected to bending and shear, we are capable of calculating just by plugging what is the value of this principal tensile strain into the general formula. We are able of calculating what is or determining what is the value of the efficiency factor. This allows, in any case, to do a bit more or an assumption also on the angle. And for practical reasons, for convenience, there are standard values, constant values that have been provided within the code as a first level of approximation.
Miguel, 3 minutes.
Yes, I will be in 3 minutes. So with respect to nodal regions, there has been a lot of work also. It has been concentrated on CCC nodes. I think this is something we already know, and there is no detailed check of the stresses, but this is allowing us to know what is the size that we have to give to our node. There has also been a lot of work on the CCT nodes, particularly these are the classical solutions where we are having anchorage outside, but also solutions where anchorage is starting inside the nodal region. And this is modifying what is the level of stress and the size, if you want, that we are requiring in the support. Also, same considerations apply to CTT nodes, and even there has been a door open to DTT nodes. These nodes, they are normally not used, but they are declared that can be used provided that there is a consistent value, good value of the efficiency factor. But in any case, they do not hold specific rules. Then I will not have time, but just to show you that you will find what is a real example that has been done with the provisions we gave to an engineer, Antonio Garcia, working in a consulting company in Switzerland. And you may follow what is the process that we can do by using these provisions. So from what is the conceptual work that we do with architects, with other specialists, and how we identify what are the regions which are most sensitive, and how, starting from equilibrium solutions as this one, this is very important that we start from an equilibrium solution, otherwise it's pointless to start doing a strut and ties. And when we have compression or tension, which is going outside of the element, we may deviate it so that it enters inside. Then we investigate what are the critical regions where we have angles that might not be allowed. On that basis, we refine again, and then we are introducing, seeing that we need some additional reinforcement to have suitable angles. And eventually, on that basis, we decide on the detailing that you may see here. And also, we see that this is a strut and tie model, and from time to time, it is interesting just to check that we have sufficient space to do locally, check, verify, the stress fields. And also, as a consequence, you may see also that adding other reinforcement and other considerations might be suitable. And this just this was the final design, but also just to show that with the same provisions, you can also go ahead and you can do a refined assessment. So with a continuity, I would say from the conceptual design, from the detailing, and even if one needs to assess. So I think that was all. Thank you very much, Jesus. Thank you very much, everyone.
Miguel, I apologize again, pressing all of you. And well, I forgot to say that you are also Deputy Director of Research, Innovation, and Doctorate in this school. So there are small room for 1 or 2 questions because Miguel has to leave. Please, John.
Thank you very much for your presentation. I wonder if you could just comment a little on anchorage issues in relation to strut and tie models. Obviously, strut and tie models, the transfer of force to the reinforcement is concentrated in the loads, yes, which is not entirely accurate. Second point is that at a CCT node, as you showed it, as you showed it at one point earlier, you have got a part of your anchorage length within the node is subject to transverse compression.
Exactly.
And then the remainder is not subject to that Now, the detailing rules don't actually allow for that.
Yeah, exactly. Let's say the classical approach is this one, so that we are considering that the transfer of forces is done outside of the nodal region. Let's say this is a lower bound, if you want. It's true that current provisions and current provisions of Eurocode, they were already allowing for partial anchorage already inside the nodal region. We have this beneficial effect, this confinement, that it is enhancing. It's about 30% of improvement. And what is allowing is that we are having this region is already transferring a part of the forces, and the rest will be anchored outside. What is the point that we have to say is that the stresses that we are having in the state of stress is a bit more complex. And this is why the limiting stress of the strut, which is coming to the node, which in this case would be this one, because this angle might be lower, then is the one governing also the size that you're having here. As you see, it is a bit larger than this one. So this philosophy also applies by extension to other cases. So this is, for instance, another concentrated node which has the anchorage outside, but also can be assumed to be developing in a smeared manner. So inside let's say that the nodal region is defined by the anchorage length. Exactly. Thank you.
Yes. Peter Tanner, please. Now I have seen you.
Thank you. We have heard now about mechanical models which can be used for assessment and design, which is very nice. We have heard about the adjustment of partial factors, which is also very nice for assessment. And both things are, of course, linked, and we need the correct input data. So do you have an idea about model uncertainties for these kind of stress field models?
Yes. Yeah. Well, yes. Well, this is a large work. I have not taken numbers, Peter, here, but I may send you, if you want, some publications where we have done systematic comparisons of rigid plastic solutions, or even enhanced rigid plastic solutions, and also elastic plastic stress fields. And these have been the basis to check what is the coefficient of variation of the model, and then to assess that it complies, let's say, within the standard values that we accept. Yeah.
Well, thank you very much.
Thank you.